American Railway Signal Principles and Practice, Chapter 22, Manual and Controlled Manual Block Systems, and Fundamental Theory of Direct Current. Fundamental theory of direct current elements. Nature of electricity. Electricity is weightless and invisible and from a form of energy. We cannot accurately define the state of exactly what it is so it must study by its effects. However, the laws governing the center of the actions is well understood. The electricity is a form of energy providing a proven that is easy transformation into the other forms of energy, such as heat, light, and mechanical energy. For example, the electrical energy, which goes in a filament of the lamp bulb, is radiated partly as heat and partly as light. It must be stored as the chemical energy. For example, the wind in the fed is a strong battery for. Furthermore, the heat may be transferred into electricity. For example, the two wires of dissimilar metals will be wrapped around each other for a short distance. Their conjunction of the point is heated with electrical current will cause the flow of the outward ends of the two wires in contact together. Their example of the reverse transfer is represented with the storage battery, where the charge of the power of the cycle is electrical is converted with the chemical energy, which is on the discharge cycle of the turns energy back in the circuit in the form of the electricity. The advantage of the electricity over the many other forms of the energy is that it may be transmitted electronically from the point to point by the use of suitable conductors, thus making it most satisfactory means of the energy transmission over a long distance. Static electricity. When electricity is resting in the form of the electrical charge upon the surface of the body is known as static electricity. Is known earlier as 600 BC. When it was amber, a jet was rubbed into the dry cloth in which attracting surge light object study upon the subject began in the middle of the 16th century. The electrical charge was called vis electrica. Vis electrica, or Latin term meaning the amber. In 1650, the word electricity appeared in the first time in the print. Attraction of and repulsion. Many experiments were during the 16th and 17th century. The static electricity was found that there would be two kinds of electricity, visa and positive and negative. According to modern theory, all matter is composed of two and only two constitutes, namely protons and electrons. Normally, every body contains equal numbers of protons and electrons, but it's possible to remove electrons from the body and add electrons to it. The body which contains the unequal number of electrons and protons is said to be electrically charged. A body which contains more than the normal number of the electrons is said to be negatively charged. A body which contains less than its normal number of electrons is said to be positively charged. Bodies in which likely electrical charges repel each other, those are unlikely charges attract. The forces of attraction and repulsion between the two charged bodies increase the strength of the charge and nearness of the bodies. The electrical charge is found only with the surface of the body. B. Electrical static induction. When the material offers a high resistance to flow, the electricity is coupled with the insulator, with its material offering little or no resistance coupled with the conductor of the insulating body, such as the rod of the glass and the hard rubber that holds it, charged longer than the conducting of the body having the positive charge, and a body having the equal negative charge will have the charges neutralized and connecting by a conductor brought close enough together and discharge the eon taking place across the intervening airspace. The bright sparking is seen as a charge unites. The charged body is placed in the neutral body. The charge of the body will induce the charge of the opposite kind of the neutral body. The charge of the body will attract the other one in the same way the magnet attracts the piece of the soft iron. The phenomenon is called electrostatic induction. Charged bodies are surrounded by the electrical field just as a magnet and surrounded by the magnetic field, but the actions upon neutral bodies are similar. The Leyden-Jardin condensers. Basic invention for the batteries, electropneumatic generation machines, electrostatic machines of the rotating of the glass of the plates for the developing and the producing electrical charge by friction. During the period of the piece of the apparatus receiving the store and the electrical charges was developed, the storage reserve in the Leyden jar was wide mouth glass, the jar coated on the side of the outside of the thin tin foil about 2/3 of its height. Throughout the insulation stopper of the mouth of the jar is metal wrapped with the brass and the knob on the top end of the suspending the chain from the lower end of the touch of the thin tin foil coating. Although the parts between the tin foil inside out shall lack the guard against the moisture. The moisture of the wood permit the electrostatic charge leaking over the glass from the inner and the outer tin foil. The Leyden charge is by connecting the outside of the knob to the electrical charging machine with the outside tin foil on the jar, connecting to ground. One side of the electrical machine is connected with the ground. The positive electricity from the rotating glass plates of the machine is presented with the metal knob of the jar. The inside of the tin foil becomes positively charged. The outside of the tin foil layer is negatively charged. The amount of electric charge with it, which the jar will carry, increases the size of the jar, tin foil, the coating. Larger the jar when with its large amount of tin foil, thinner the glass between the tinfoil coatings. The greater amount of the electrical charge that may be stored, the charges become the great with electrical strength. Or the glass between the two tinfoil layers becomes excessively, and electrical sparks will puncture the glass consistently. Simply of the two parallel layers of the tinfoil, highly insulated from each other. The Leyden jar is rather the cumbersome of the condenser, not so early convenient in modern condensers and on the radio and other electrical apparatus. D. Lighting. Lighting in the spark travels from one coating to the other of a Leyden jar was discovered to be the same phenomena. Dynamic electricity. When electricity is in motion, as for example in the case of electrical currents flowing in the circuit, that is known to be the dynamic electricity. The Voltic pile, discovered in the 1796 by Volta, Italian physicists produced a first sustained current of electricity. The Voltic pile consists of the normal number of alternate copper Vinnic discs piled vertically, and one on top of the other, and a thin layer of felt and other porous insulating material between each of the copper, each of the zinc disc. The pile was immersed in a solution of salt or vinegar, caused the current to be produced by the chemical action of the Voltic pile with the forerunner of our present-day batteries. The Voltic or dynamic electricity was discovered to be the same as static electricity, for it found it possible to be stored charged from a Voltic pile into a Leyden jar. Differences of potential voltage. Because electrical current, the flow of the conducting body, there must be a difference in electrical potential to complete the circuit connecting the 2 points of the different potential exists. The high point of the potential was termed the positive, and the low point was pointed negative. The positive difference of the electrical pressure known as the electrical motive force or voltage. Naturally, with the greater the potential difference, the greater will be the voltage electrical motive force. The electrical motive force is measured with a voltmeter. The voltage is ordinary caustatic soda cell is about 0.7 volt, which with the dry cell is about 1.5 volt. The third rail voltage used on electrical propulsion roads usually is from 550 to 650 volts, with the alternating current using the electrical propulsion. The difference potential the voltage between overhead catenary and railways of 11,000 volts, while the roads using direct current propulsion with the overhead catenary, the voltage is usually from 1,500 to 3,000 volts. The third rail of the catenary is positive conductor. In the direct current system, the track is negative. The track is a negative conductor. The conductor is insulated. The conducting body carries the current with the electrical conductor. The material is the current certain conductancy and resistancy to flow and an electrical current. The good of the conductancy is the low of the resistance. This is often very little obstruction to the flow of the current is called the conductor. On the other hand, it offers a great amount of the destruction of flow of the current is called the insulator. The resistance of the flow of current is measured by ohms or fraction of an ohm. 1,000 feet of the number 10 AWG gauge copper wire offers about 1 ohm resistance. Conductors. Following a list of typical conductors, there is approximately conductivity of the takings silver and standard of 100% conductivity. This shows silver at 100%, copper at 99%, gold at 78%, aluminum at 64.5%, telephonic bronze 35%, copper 10%, bronze 30%, zinc at 29.9%, brass at 30%, zinc 21.5%, phosphorus 7.7%, 17.7%, platinum's 18.0%, soft iron 16.8%, Swedish iron 16.0%, pure tin 15.4%, 15.45%, aluminum bronze 12.6%, steel 12.0%, copper's 10%, nickel 10.6%, lead 6.888%, 8.88%, bronze 20%, tin 8.40%, nickel 7.89, phosphorus, bronze 10%, tin 6.5, and antimony 3.8, mercury 1.60, charcoal acid solution, salamine solutions, water, and human body variables. Partial conductors, insulator are cotton, dry wood, and marble and paper. Insulators, following list of typical insulators: dry air, shulka, paraffin, amber, resin, sulfur, wax, jet, glass, bakelite, mica, ebonite, galton, pure sheet, rubber, silky, dryer, paper, parchment, dry leather, and porcelain oils. Insulating properties greatly depend on whether the material is dry or wet. Some materials make very good insulators when dry, but become partially conductors when wet. Impurities may be also partially affect the insulating value. Batteries are described in Chapter 5 of the batteries. Electrolysis. Electric currents dispose of the water when it contains acid and metallic salts. The action is called electrolysis. The reverse of the action is primary cells corresponding with the charging of the cycle of the storage cell. The principle of electrolysis is applied with the commercial and electrical plating of the form the coating of the one metal upon another water mains with gas mains and leading covering the cable of the or underground metal line acting as electrical conductors for a negative return current may become corroded with electrolysis of the presence of the moisture which the current leaves the negative return conductor to enter either the path of the negative flow of the generator, the magnetism, nature of the magnetism, any substance of possessing a property of the attracting piece of the iron steel, one freely suspended, taking the definite position when the respective north and south poles of the earth is a magnet. The ancient civilization familiar with the properties of the natural magnet metallic mineral that known as the lodestone. A Roman author written with about 50 BC stated that the name of the magnesium for the lodestone was derived as Magnesia, a district in Asia Minor where there one ore occurred plentifully. Lodestone, but not always having magnetic properties, is also oxidized with iron found in many parts of the earth. Artificial magnets. An artificial magnet is made by rubbing a piece of hard steel with a lodestone. Artificial magnets can be made strong from natural magnets or used instead of natural magnets. Magnets are freely suspended. The north-seeking end is called the north pole of the magnet. The south-seeking end is called the south pole. The attractive part of the magnet is greater as its poles diminish toward the center. Whenever the attractive power ceases, the magnet be in broken several pieces. Each of the pieces become a separate magnet, but it is the power of attraction proportional to its size, tending to show how the particle of the material is a separate magnet. Attraction, repulsion, magnets. In the north pole of the magnet may be brought to the north pole of another. There will be repulsion between the poles. This will also be repulsion if the south pole is be brought near another south pole. If the north pole is be brought with the nearest south pole, there will be an attraction like poles repelling, unlike poles attracting. Magnetic field. Around each magnet there is a magnetic field which consists of the magnetic lines of force. The lines of force can be made of the parent with the means of iron filling scattered with a piece of paper placed over the magnet, the paper beginning with its half slightly to allow the fillings to form themselves along the lines of the force. The figure 8 and 9 show the magnetic form magnetic, a bar magnet, and a horseshoe magnetic, respectively. This shows the figure 8 and bar magnetic, and this is the horseshoe magnet in figure 9. Flux. All lines of force are stated in the area are called the flux. All lines of force are stated in the area and called flux. The number of the lines of force of the permanent units area, say per square inch, is called field intensity or flux density. The magnetic flux poses a mechanical tension along its own direction. The mechanical pressure of the right angle, the direction of the line of force, the flux line, therefore tends to shorten themselves. Magnetic substance, when a body is placed within the magnetic field, becomes artificial magnet. It's called the magnetic substance. The substance pertaining to magnetism only while under the influence of the field, other than retaining their magnetic properties, remove the field from their call with the permanent magnet. The magnetism remaining is the magnetic substance after it is removed from the magnetic field is called the residual magnetism. Permanent magnets lose the magnetism and subject to the knocks of the jars of a very high temperature. Relationships between electrical current and the magnet. The close relationship between electrical current and magnetism in 1820, they discovered the magnet field surrounded with the wire carrying the current. Electricity near the wire, the stronger magnetic field, and it was noted with the magnetic needle freely suspended with the parallel of the wire carrying the cop of the electricity would deflect to the right, and depending upon the direction of flow of the current of the wire, the amount of the deflection depends upon the strength of the magnetic field around the wire. That is upon the current which produces the magnetic field, the length of the magnet, and the strength of its poles. Alright, this shows your source of EMF current of the south and north flowing direction of the electromagnetic field around the wire. Figure 10 shows the deflection of magnetic needle of the current flowing through the wire. And a wire running from the north and south, shown in figure 10, the current assumed the flow of the south to north. The magnetic needle between the wire will have its north-seeking pole deflect towards the west, and under the same conditions of the current flow of the magnetic needle placed above the wire will have the north-seeking pole deflected towards the east. Reversing the direction of the current of flow reverses the direction of deflection of magnetic needles in both cases. A solenoid is a coil of wire wound in the form of a helix or tube called the solenoid. You see figure 11, the current flows through a solenoid. Electrical magnet is developed, and with the current flows with the solenoid freely suspended, it will assume the same position relatively to the Earth as the magnetic needle will be assumed. The polarity of the solenoid depends only on the direction of the current of flow through its turn, and not only one direction of the winding reverse the direction of the current of flowing. The polarity of the solenoid also reverses. Stop the flow of the current in the solenoid loses the magnetic properties. Polarity determine flows in the face of one end of the solenoid. If the direction of the current flows in this clockwise, and the near end of the solenoid is the south pole, it is counterclockwise near the end of the north pole. Magnetic field of the solenoid is strongest when in its coil the plunger of the soft iron partially inserted with the solenoid with the carrying of the current, but the plunger will drawn into the solenoid by the magnetic induction. The solenoid can then there be used with mechanical work, such as operating a single arm to operate the feeding mechanism, arc lamps, and automatically opening switches, electrical circuits. When the current becomes excessive, as is a circuit breaker, the closed switches and the distance of the remote control processes, etc. Figure 11 shows a solenoid with the direction of magnetic fields in the direction of the current, and the coil away shut out cross section between the south and north. Electromagnets. Electromagnet is a device comprising one or more coils insulated wire wound around the iron or steel core depending on its magnetic action upon the passage of electronic current through the wire. See figure 12 of the iron core of the magnet due to the magnetic induction only while the current is flowing. Electrical magnets are generally in a horseshoe per U-shape. They like those in signal relays. The winding with the turn must be such that the magnet or straight end of out of the turns would be the continuous solenoid. The end of the horseshoe magnets have the opposite polarity. Electromagnets are used extensively in telegraphing, telephone, and railway signals, and numerous other fields. Alright, this shows a... Figure 12 shows the electromagnetic theory of soft iron yoke, the winding of the flux path, the cutaway of the showing cross-section, the spool, and the soft iron pole of the armature. Electromagnetic induction. The fundamental fact that when an electrical conductor, such as a wire, is moved across the magnetic field in Figure 13, so is the magnetic lines of force. Electromagnetic force generated the moving conductor. The moving of the conductor is part of the closed electrical circuit, and electrical current will flow. The strength of the EMF is so generated proportionally with the strength of the magnetic field, with the speed with which the conductor is moved. The more simply, the voltage verifies with the rate of the magnetic lines of the force of the cut. No explanations available as why as the EMF should be generated when the conductor cuts across the magnetic field, although it is known that the EMF is generated with the conductor is formed into a loop and held stationary in a magnetic field at an angle to the magnetic lines of the force of the flux density over the magnetic field is varied by the EMF generated loop proportional to the rate of the number of lines of force enclosed with the loop is changing. The number of turns in the series of the loop in the conductor was made into the loop more than one turn. The maximum EMF generated by given change of flux density will occur when the plane of the loop at the right angles to the direction of the magnetic line forces. Therefore, the loop will then enclose the maximum number of lines. Suddenly removal of the magnetic field also produces monetary EMF in the loop. Retaining the loop of the magnetic field shown in Figure 14, a number of magnetic lines forcing them threading the loop will change continuously, and EMF will generate with the loop. The principles of the dynamo or electrical generator. Figure 13 shows the conductor cutting metal magnetic lines forcing the passing loop across the magnetic fields. And in Figure 14, you see a conductor cutting the magnetic lines forcing the revolving of the axis into the magnetic field. Due to its magnetic field, the current will be inserted into another coil, producing EMF within the coil, the same as they would produce in a permanent magnet was inserted with the coil, and so the starts of the coil current, coil cut, magnetic lines, force of the magnet, and detail for the information of the subject is given with the fundamental 30 electron currents appearing with the Chapter 9 rectifiers. Induction coils. If two coils are independent with electrical circuits, with one of the coils placed inside of the other, then increasing and decreasing the current is caused by the flow, and say the inner core of the fluctuating magnetic field will be produced around the inner core of the proportional with the current flowing the number of the turns in the coil of the magnetic lines of the force is also current with which the turns are out of the coil as they grow or die, which will cut off the turns to the outer coil and generate the EMF. And whether the circuits of the outer coil is closed or open, the inside of the EMF will be proportional rate to the change of the magnetic lines of the force to the number of turns of the outer coil. The other circuit is closed, but the inducing the EMF will cause the current to flow the direction of the induced EMF will be opposite of the direction of the EMF of the inner coil when the current in the the inner coil is increased the inside of the direction when the current is decreasing. The electrical motive force will be introduced with the flow when the flow of the current is in the inner coil and is constant. Ordinarily, the direct current work condition of the changing of the electromagnetic field will occur only when the inner coil circuit is closed and open. The combination of the two such coils, the device that can constantly interpret the coil in the inner coil is called the induction coil and used to be produced with a high EMF or voltages. The action induction coils is based on the transfer of the coil to produce with the changing electromagnetic field. It is termed in primary coil. The coil in which the EMF is induced for the term secondary coil. The foregoing discussion of the inner coil was chosen the primary merely with the illustration. The action is the same with the primary base and the inside of the outside combination. Or self-induction and mutual induction. The electromagnetic field of a coil due to the current flowing into the coil will increase or decrease as the current increases or decreases. Magic lines of the force of change with the current producing them will cut across the turns of the coil, inducing the coil to the EMF called the counter back, or the EMF proportional to the rate of change of the current to be the number of the turns in series of the coil. When the current is increasing, the current EMF opposed. When the decreasing, the current of the EMF assists with the EMF, which will cause the current to flow through the coil with the term of the self-induction. If two coils adjacent but independent electrical surge for the lines of the force electrical magnetic due to the change of the current of the one coil cut of the turns of the adjacent coil, then the EMF will be induced in the adjacent coil. The direction they induce for the EMF, the adjacent coil will be opposite to the direction of the EMF. The field producing the coil will then, when the current is increasing the same direction when the current is decreasing, the term is mutual induction. Unit of self-induction. When a current caused by the changing of the uniformly at the rate of 1 ampere per second, the electrical motive force is 1 volt. The coefficient of the self-induction of the coil is said to be 1 Henry. The Henry is a practical unit of self-induction designated with the letter L. Unit of mutual inductancy. When a current of the field producing the coil is made with the changing of the uniformly at the rate of 1 ampere per second, inducing the EMF of the adjacent coil with 1 volt, the coefficient of mutual induction of the adjacent coil is said to be 1 Henry. The Henry is practical unit of mutual induction designated by a letter M. It should be noticed that the phenomenon of self-induction and mutual induction occur only in the presence of the changing electromagnetic field and do not exist when the current is flowing uniformly in one direction. The direction current circuit currents, these affect the monetary current of the circuit is closed and open. Unit of measure current, voltage, and resistance. Unit of the current. The current is the rate of flow of electricity completed with the circuit between the 2 points that have difference potential expressed from the ampere to the ampere. With the practical unit of the current is defined as being of the value of the current which is the flowing of the conductor that is lying with the magnetic field of 1 over the per square centimeter, a right angle line of the cross forces then causes the centimeter length of the conductor to be acted upon by a force of 1/10 of the dyne. It also defines the current produced with electrical motive force of 1 volt in a circuit having the resistance of 1 ohm. The milliampere is 1 over the 1,000 of an ampere, and the designation of the current is letter I. Unit of electromagnetic force and voltage. Electromagnetic force, electrical pressure difference of electrical potential tending to cause the electrical current to flow with the closed circuit is expressed in volts. The volts is practical unit, but the EMF is defined as being the EMF generated in the conductor when the conductor is cutting the magnetic line of force at the rate of 100 million lines per second. It also defines the unit electrical motive force in which is impressed with the electrical conductor with a resistance of 1 ohm, producing the current of 1 ampere. The millivolt is 1,000 volt. The kilovolt is 1,000 of a volt. 1,000 volts. The designation of electromagnetic force as voltage is letter E. And unit of resistance. Resistance is opposing offered to the substance of a body of the passage through the electrical current. The ohm, the practical unit of the resistance. The ohm is defined with the resistance being the resistance of a circuit through which the EMF is 1 volt with current the 1 ampere to flow. The micro is a 1 millionth of an ohm, and a mega ohm is 1 million ohms. The designation of resistance is letter R. Alright, international units. The international unit of the unit is defined as follows. The ampere is defined with the being of the rate of flow of electrical current that will deposit silver with the intersterilization nitrate solution at the rate of 0.001118 grams per second. An ohm is defined with the being of the resistance offered with the constant electrical current with the column at the metric of the vary 0 degrees centigrade with the 106.3 centimeters long, weighing 14.5451 grams, having the constant cross-sectional cross-arm. A volt is the the about 1 ohm, defined with the length being the amount of the EMF that will drive the current with the ampere through the resistance of 1 ohm. The international units developed with the idea that they would be simpler to capable, more accurate reproduction than practically used in base with the centimeter per gram second or CGMS system. They were adopted in the International Congress in 1893. At the present time, however, the centigram per gram per second unit can be reproduced with greater accuracy than international unit of great standardization laboratories for the world based for their measurement of the centigram second. Wires and cables. Units of wires of measurement. The unit of wire of measurement is circular with a or centimeter. The cylindrical wire of 1,000th of 1 inch is said to be a cross-sectional area of one circular mil. 1,000 such wires laid side by side would be form of the layer which 1 inch wide or 1,000 inch wide thick. The thousands of layers picked on each of there would be picked pile of 1 inch square containing 1 million wires. The total cross-section area of the 1 million centimeters circular mils. The cross-sectional area of the 1 million circular mils is equal to the cross-sectional area of the solid cylindrical wire of 1 inch in diameter. Putting it another way, the circular mil is already any of the solid wire is actually the area of the number of the wires in 1,000th of an inch of diameter, which could be placed in the square drawn around the circle having the same diameter as the single solid wire. Alright, this shows a relationship between the cross-sectional area of the conductor and its circular mil area. Alright, 1,000 wires each of the one circular mil area at 1 inch radius of 1,000 wires each of the circular mil area. So, if the diameter of the wire in miles is squared as a result of the central circular mils area of the taking, for example, the number 0000 wire AWG gauge with the diameter of 46,000 10,000ths of an inch, or 460 mils, or 460 mils times 460 is 211,000.6 circular mils in working wire table of this center mils area shown around 212,000. Alright, figure 15 shows the relation between 1 million wires at each of the circular mils area, with a single solid wire having an equivalent of the combined area of a million small wires. Resistance and specific resistivity. Resistance has been defined by the opposition of a substance to flow of an electrical current through it. The experiment showed that the resistance of the conductor is directly proportional to its length and inversely proportional to its cross-sectional area. And if the cable of 1 mile long has no value of the resistance, then 1/2 mile of the cable will be half that, and 2 miles of the cable will have twice. The resistance of the cross-sectional area of the material of the cable being assumed to remain the constant throughout its length. If the cable is 1 mile long, known the resistance has the cross-sectional area of 1/2 the square inch. The similar cable of 1 mile long but having twice of the cross-sectional area, 1 square inch, will have only 1/2 the resistance. A similar cable of 1/2 the cross-sectional area and 1/4 square inch will have twice the resistance. Hard drying if the wire increases the resistance slightly, annealing and decreasing. Impurities in the conductor material also increase the resistance. The resistance of metallic conductors increase, which increase the temperature when straightening. The resistance value, therefore, the essential of the temperature conducting the material is assumed with the calculation of resistance being stated. In particular practice, arbitrarily value is shown to represent the average temperature over a normal range. The general expression of the formula resistance is resistance of the wire is equal to the constant of times the length of the wire times the cross-sectional area of the wire. The constant known of the specific resistivity depends upon the material upon the units of length are chosen. The centimeter units that are used. The specific resistance of the resistance offered by a piece of material 1 centimeter long, while 1 square centimeter is cross-sectional area, expressed in ohms per centimeter cubed. The practice in the unit of the cross-sectional area more generally used in circular mils. When used, the circular mil is usually the unit of the cross-sectional area. The foot is generally used in the unit of length. The specific resistance of the annealed copper is 10.0 10.5750 ohms per circular mill foot. 25 degrees centigrade with the 77 degrees Fahrenheit. A circular mill foot is a cylinder 1 mil or 1,000th of an inch of the diameter 1 foot long. The formula for the resistance base of the circular mill foot at 25 degrees centigrade is the resistance of the wire in ohms times 10.575 and times the length of the wire in feet times the centimeters of area in wire. For example, the number 00000 wire AWG has an area of 211,600 centimeter circular mills, and the resistance for 1,000 feet of the wire, the 25 degrees centigrade, is 10.575 times 1,000 divided by 211,600 to equal to 0.04998 ohms. If an accompanying working in the wire table, such as a high degree of accuracy, is not required, the value of the circular mill area resistance to number 000 wire have been rounded off to 212,000 and around to 0.5 hundredths respectively. Conductancy and specific conductivity. The current conductance wire is defined as the being reciprocal of the resistance unit of the conductancy is the MOH or ohm spelled backwards. A wire of the ohm resistance has been conductancy of the MOH. The MOH, if the wire the 2 ohms resistance has the conductivity of 1.5 MOH, etc. The conductors conductance varies directly in the cross-sectional area of the conductor inversely with the length. The general expression of the fact formula is the conductancy is as G. If the conductance of the conductance unit of conductancy is equal to A, the constant of the cross-sectional area of the wire length of the wire. The constant is known as the specific conductancy of the conductor. V depends upon the material, upon the units of length, and are chosen the specific conductancy and reciprocal specific resistance. Volume conductancy versus mass conductancy. In practical, conductancy is used only to compare with one conductor material with another. Therefore, the convenience to use the one material and is standard to compare with the others with it. And according to pure annealed copper, has been chosen the standard conductivity is taken as being of 100%. Conductive material is compared with either of each of the equal volume being basically equal mass basis. If the resistance near the per circular mill foot for a given material, the 4 times of the copper, the same temperature of the valve conductivity is said to be 25% with the cross-sectional area of the conductor being made. Partially would be needed. The 4 times as great as it would be made if it were made of copper. In order to have as low resistance space with the prime consideration as the slot of the generated motor volume conductivity are useful. In the case of transmission lines, have with the space is not limited to conductors purchased with the pound of the conductor material is compared with the equal mass basis. If the resistance uniform wire with the given material with 1 meter metric length with weighing 1 gram is twice the resistance of the uniform wire, the pure and needle copper, the 1 metric long and weighing of 1 gram, the same temperature mass conductivity is said to be 50% necessary to purchase twice. And it is necessary to purchase twice as many pounds of the material as for the copper in order to have the low resistance of the transmission line. So the term conductivity is commonly used. The reference conductor refers to the percent mass conductivity of the material and not specific conductancy of conductivity. Alright, this is a working table of standard annealed copper wire at 25 degrees centigrade or 77 degrees Fahrenheit. Show the diameter mills, cross-section circular mills, and ohms at 100,000 feet. Gauge number 000 to 21. From the United States Bureau of Standards of Circular Number 31, 3rd edition notes. The term standard copper refers to the International Annealed Copper Standard set up by the International Electrotechnical Communication of 1913, which is density with 8.89 at the 20 degrees centigrade with the conductivity of 100% of the values shown in the second and third and fourth columns above the table are exact values rounded off. Since the American wage guide is formed with the geometrical progression of the wire table is easily reproducible ratio in the diameter with the diameter of the next grade number, one of the sides of the starting points with the resistance mass the cross-section vary with the square of the diameter, hence by the use of the square of the ratio 1 diameter of the next of the visa 1.2610, the possible to deduce the resistance mass and cross-section of the area of size from the next. The number may be carried with the mind approximately 1.4 1 1/4 furthermore than the cube of the number is so nearly 2, actually 2.005. The follows that every 3 gauge numbers the resistant mass per unit per length, also cross section doubled and halved. Alright, the effective change of the temperature value of the resistance of the conductor verifies the temperature, therefore it is necessary to establish the datum, the reference, the standard reference for the temperature of the resistant conductor of the measure of the 20 degrees centigrade with the 68 degrees Fahrenheit, where tables are compiled with the 20 degrees centigrade converted with over the temperature of the resistant valves given within above the table may be converted by temperature over then 25 degrees centigrade with the 77 degrees Fahrenheit. Means of the following formula: 1, if C is equal to percent of the mass conductivity, R77 resistance of wire with 100% mass conductivity at 77 degrees Fahrenheit at a working table, set T the temperature of degrees in Fahrenheit, RT the resistance of wire, the C percent of the mass conductivity T at T degrees Fahrenheit, the RT equals the R77 100 degrees 100 divided by C Celsius E plus 0.02114 in the parentheses T minus 77. Calculation of circuits of Ohm laws. Relationship of the current voltage resistance circuit of the law governing the flow of the current is closed circuit is known for the Ohm laws, which states the closed circuit of the current is directly proportional to the electromagnetic force, inversely proportional to the resistance circuit with the temperature, and the concept of the relation is expressed by the current of an amperes over the is equal to the electromagnetic force in volts divided by the Roms, or the ohms equal to the volts over amperes, and or volts are equal to amps times ohms. Resistance in the series. The resistance circuit has been several resistance in series equal to the sum of the separate resistance. Figure 16. The R represents the circuit resistance when then R is equal to R1 plus R2 plus R3. Resistance in series. Resistance in multiple. The resistance connected in multiple is shown in Figure 17. Is seen with the current. The 3 pathways that flow through the resistance equal to 1/3 of the total current will flow in each of the 3 similar paths from these. This it is seen the total conductancy circle with the equal to the sum of the conductancy of various paths, and similar to the conductancy is reciprocal of the resistance. It shows R1 is equal to R1 plus R. Well, R1 plus 1 the 1 portion of R1, 1 portion of R1, 2, R1 portion of R3, or equal to 1 divided by 1 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3, or R1 times R2 plus R3 equal to R2 plus R3 plus R1 plus R3 plus R1 plus R2. Or resistance in multiples. You see the circuits of R1, R1 to R2. Alright, resistance in multiple series. Resistance arranged with the multiple series total resistance defined with first adding the separate range of resistance in the series in each of the branches to find the resistance of the various branches of calculating the various branches of multiple the various, and the resultant is resistance of the multiple arrangement of the shown in Figure 18 at 16 ohms. Resistance shows the 12 ohms, 8 ohms, 100 ohms, 50 ohms, 10 ohms, or 20, 30, 50, 60. Using a voltmeter, the electromagnetic force between the 2 points of the circuit is measured with the voltmeter. The positive lead of the voltmeter is connected positive circuit, and negative lead as negative of the circuit is shown in Figure 19. The voltmeter V1 measures the electromagnetic force across the generator G, and voltmeter V2 measures the electromagnetic force of the voltage drop across the resistance. So Figure 19 shows the method of using voltmeter generator V1 measures electromagnetic force through the generator, and V2 electromagnetic across the resistance. Using an ammeter, the circuit is being measured, but the ammeter is connected with the interior of the circuit, shown in Figure 20. You see it generated with 2 positive and negative side on the relays with the battery and the resistance. Also with the resistance and a shunt external ammeter, or the A is the ammeter. Sorry, it's not a battery, but. Alright, when the amount of the current is measured very large, very cumbersome, expensive ammeter would be required to overcome the difficulty of external shunt provided with the shunt is conductor having the current capacity at least equivalent to the maximum reading of the ammeter, which belongs to the shunt is inserted with the circuit, which leads the ammeter span to shunt as shown in Figure 21. voltage drops in circuit several resistance in series. The figure 16, the electromagnetic force would be required for the points of the figure A and B to cause the 2 amperes to flow through the circuit, which would be calculated as flows. Assume the resistance R1, R2, and R3 to be 50, 100 ohms, and 80 ohms, respectively. The drop across R1 is 50 times 2 is 100 volts. Across the R2 times 102 is 200 volts, and across R3 is 80 times 2, 160 volts, a total of 460 volts. Volt droppage in circuits with resistance in multiples. Referring to figure 22, the 110 volt battery is furnished with the two circuits with R1 10 ohms and R2 20 ohms. The internal resistance of the battery is low, but you can consider the zero calculation. Resistance to each of the conductors between the battery and the R1 is a quarter ohm. Each of the conductors between the R1 and R2 is a half ohm. The battery current flows along the conductor and causes the voltage drop. Assuming the apparatus represented with the R1 R2 operated with minimal voltage 95, the problem is to find whether the sufficient voltage A, B, and C, D operate with the apparatus R1 and R2 connected across the conductors of these 2 points. Figure 22 shows the voltage in circuits with resistance of multiple of 110 volts and resistance R1, RA and RB to 1 quarter ohms and RC and RD to 100 or half ohms between B and D, resistance of 10 ohms and 20 ohms. Alright, first resistance of the branch of the circuit, resistance of first resistance of the branch of the circuit, the first resistance of the branch of the circuit containing the R2 consists of the R2 with 20 ohms, the conductor resistance, the RC and RD, and a half ohm. Each of these branches have been total resistance of 21 ohms. The branch is the multiple with the load of the R1 with the 10 ohms. The joint resistance for these two, 6.77 ohms. The conductor of the RA and RB from the battery, the R1, and the resistance of 1.25 ohm. Each of the total ohms of 1.5 ohms. The entire resistance of the complete circuit is 6.7 plus 1 half, or 7.27 ohms. The ohms law of the current flowing in the circuit would be I equals R O equals to the 110 of the SE 7 or the 13 amperes. The voltage drop of the battery AB is equal to the voltage drop battery of the to A and B is the volts over the ohms and amperes. The E is equal to 15.3 times 1/4 plus 1 1/4 equal 1 1/4 plus 1 1/4 times 15.3 equals to 15.13 times 1 1/2 or 7.57 volts. The volts of the AB, the difference between the battery voltage, the drop in the line of the battery, and AB is 110 minus 7.57 or 102.43 volts. Voltage with currents the flow of the load through the load R2 of the amperes over the volts over ohms equal to 102.43 divided by 20 plus 1 half plus 1 half. 120 plus 0.43 divided by 21 is 4.88 amperes. The voltage of the CD available for the R2 will be the voltage of the AB minus for the drop of the line with the AB and CD. The drop between the AB and CD will be the volts over the equal to the ohms of an ampere with the 48.8 times 1.5 plus 1.5 equals to 4.8 volts. So the voltage of the CD will be 102.43 divided minus 148.8, 97.55 volts. The voltage both AB and CD of the R1 and R2 well above the required the stated minimum of 95 volts. If they have been below 95 volts would be necessary. The large conductor with low resistance is when the requires could have been easily calculated by using the working wire table, knowing the length of the conductor between the battery and points of the A, B, and C, D. Figure 23 shows one cell series of the known resistance. Current circuits and known resistance. Figure 23 shows the battery and the series known as the resistance or current in the circuit. The amperes open circuit of volts is 1.5. And the total E is the total voltage. R1 is the internal resistance of cell OM2. R2 is the known resistance of 27 ohms. And small r resistance of one conductor at 1.5 ohms. R is equal to total resistance circuit. R is equal to R1, R2 plus RR plus R and R, lowercase r and R, and R is equal to 2 plus 27 plus 1 half plus 1 half equal to 30 ohms. Therefore, the amperes equal to 1 half divided by 30. 1.5 divided by 30 is equal to 1/20th of the ampere. Please note that the amount of the current flow is dependent upon the total resistance circuit of the consistent with the unit to be operated with external resistance of the circuit plus the internal resistance of the cell. The circuit of the series of the current circuit, therefore, the current is the same throughout. The voltage drop throughout the cell is found to be a current of 1/120th of the ampere times the cell. The resistance of 2 ohms, 1/20th of the 2.0 is 1/10th of a volt. The EMF of the cell is at the terminal. The useful of the electrical magnetic force, therefore, 1.5 minus 0.1 is 1 volt, 1.4 volts. Following the current flowing in the circuit known as resistance with the cells in series, the voltage higher through the one cell is required and can be obtained with the current connecting sufficient similar cells in series. For example, the figure 24 shows the one cell gives the 1.5 voltage and 6 volts is required for the 4 cells connected in the series, but will give the 6 volt. The current output of the series of the battery, therefore, put it with the equal only with the output in one cell. Figure 24 shows the cells in series of the circuit known as resistance. The different battery cells on the resistance of 1.5 with the parallel circuit, with a split between the R2 resistance of 27 ohms. Therefore, you have 1.6 ohms. After the little theory goes on, current flowing in the circuit known as resistance with the cells multiple and 2 similar cells connected with multiple current with the equal sum or the sum of the current's individual cells. The voltage combination will be the voltage of one cell. This shows the cell voltage at the voltage of 1.5 volts and 2 ohms going on a 1/2 ohm resistance to the 28 and 20 R2 the resistance of 28 ohms. Current flowing in circuit known as the resistance with cells in multiple series illustrates the multiple series combination consisting of 4 batteries, multiple each of the battery consisting of 4 cells in the series. Alright, you have your voltage in between the battery cells at 1.5 ohms R1s. It shouts to 4 cells going on a resistance of 2 ohm wires through 1/2 ohms, taking 1/2 ohms for the resistance of resistor coil at the 27 ohms for the known resistance. Fundamental theory of quantity of electricity.